Hello, welcome back to Statistics with Dr. Platt, and we're going to be continuing looking at ideas related to correlations and their correlation coefficient. And we talked about in the previous episode the nature of the strength of a correlation. We can also need to consider, under certain circumstances, the level of significance, or whether a linear correlation is significant or not. One way we can do this is to compare the R or rho value against a value from a critical R table, where you take your number of elements in the scatter plot and you compare it to the level of significance alpha. Another way we can do that is to do a hypothesis test, where we're going to compare the population or sample correlation coefficient, and if it is, generally it's going to be a two-tailed test. If it is statistically matched to zero, then there is no significant correlation. If it is not, then there is a significant correlation. And that R value or rho value is what we determined before. Another tool you can use is a t-test. So we find the t-statistic using the R value over the sigma sub R, or this summarizes to T equals R times square root of n minus 2 over 1 minus R squared. And we compare the T to a T critical to find out whether our T is significant. And when we have a correlation indicated by our correlation coefficient, it can imply that under certain circumstances, it can imply that a cause and effect relationship exists, but it could be the opposite direction that you believed it was. More likely, there's going to be a third variable in place to indicate the relationship. There may be a lot of complex interrelationships among the variables, or it could just be coincidental. The presence of a correlation does not imply causation, but it might suggest it. You have to do other things, generally experimental, to try to determine whether the cause and effect does actually exist. So there are a lot of cases where our correlation can become or you can make very weird correlations, such as lemon imports and car driving fatalities, which can be constructed as having a correlation. But it seems very unlikely that the number of tons of lemons imported would have any real impact on fatal car accidents. And if so, there's a lot more intermediary than just the direct one-to-one. And in order to find out a lot more about our shapes and our correlations, we have to find our line of regression. Y hat, which is our predicted value, equals M, the X observed, plus B. This is sometimes represented by Y equals A plus BX. And there's a couple formulas shown here that can allow you to find your intercept and slope. However, let's use some other tools. They can be read directly off of this add-on to our equation, to our graph, or we can do equals slope of our y's comma our x's, and we have this value for y. This is our slope, and our intercept equals intercept of C4 or C3 through C34 and B3 through B34, and it gives us our y-intercept. Our line of intercept, or our line of best fit, allows us to predict our x or y values. And on our graph, the predicted y values are on the line, and our observed y values are generally above or below it. Each of these gaps is a residual, and if done properly, these residuals add up to nothing. The amount of our residuals and the nature of our residuals can help us figure out our total deviation by looking at two parts: the difference between our observed value and our anticipated value or predicted value, and our horizontal line here is our average y value. So the difference between our y value, that is our expected, or our average y, or mean y, and our observed values is our total deviation. Our explained deviation is the difference between the predicted value and the mean, and the difference between our observed value and a predicted value is our unexplained deviation. When we add up the squares of these, we get our total variation, our unexplained variation, and our explained variation. Our explained variation is the amount of vertical distance between our mean and our expected. Unexplained is how far beyond the expected our observed are. A residual plot can be formed where we take the size of all of our residuals, and if they're randomly scattered in sort of a rectangular shape around the x or y equals 0 line, then that suggests that our correlation is pretty decent. The value r squared that we can pull up on a graph is our correlation or coefficient of determination, which is the square of our correlation or coefficient of correlation, and it is the explained variation over the total variation. The closer this is to 1, the stronger the regression, or the correlation. The closer it is to 0, the weaker it is. A r squared of 0 gives us no information, tells us that nothing is explained, where a correlation of 1.0 tells us that everything is explained. Using our line of best fit to make predictions gives us a point prediction or a single value, and it is sometimes better to have a range of values that have certain level of confidence that our actual value falls within. And that can be found using our standard error of the estimate. And it creates a predictive interval. Given to us by this formula. So we take a predicted value and multiply it by our relevant t-score, 2 times our standard deviation of our estimate, 1 plus 1 over n plus n times the x minus the x average squared over n times the sum of the squares of x minus the square of the sums of x is less than y is less than the same equation, except with a plus here rather than a minus. All right. Be back to you again with more in the near future.